Hey everybody, I wanted to talk a little bit about these Jamboards that you did today. Overall, they were really good. I want to point out one thing here, which is in this page. This group drew the object that sped up differently than most other groups. I'm not going to say right or wrong, just want to point out it was different. So if we look at this, and then you compare it to, well, this group did actually something quite interesting. They drew a velocity graph here because they interpreted what I said literally. I meant for them to be position graphs, but they drew a velocity graph. But note that their two position graphs for the low and high angle look different than that first group. This group, right, drew them like this. Their position graph like this. This group over here drew a position graph kind of curvy upwards. So it was one group, I just want to point out really, like this group as well, it was one group that had a very different looking position graph over here. I'm not here to say which one's right or wrong, I just want to kind of point out that this is a little tricky, and we'll resolve it, but it'll take a while. I want to go over now a couple of answers to questions in this, geez, in the activity you worked on today. Let's start with vectors and scalars. This group is 100% right. Velocity, displacement, force are vectors because they must point in a direction. We already talked about velocity and displacement, right? Because they have to get a direction, but force as well. You can't push an object without pushing it in a direction. And you can't really give a direction to volume, temperature, speed, distance, or time. You might say, well, can the temperature go up? Yeah, but really it only metaphorically goes up. It doesn't actually move like in a direction, right? Like, can temperature move to the right? That's not a thing. Time's also a funny one where like you might say like, whoa, wait a second, doesn't time go forwards? Yeah, but because time can't really go like, right, left, down, diagonally. It's not, we're going to treat it as a scalar, though I should admit time is a kind of funny one. Okay, I want to next talk about this over here, two different kinds of velocity. This group over here, they were a little bit too fancy pants for my blood. I don't want to call it linear and exponential. I want to use the terms I gave you before of constant velocity or constant speed and then increasing speed. Right? I mean, I assume that's what they meant, but like I just don't want to get fancier than that. Like I also don't know if like I see an object moving and someone says, oh, that has linear motion. Like I don't know what that means. But if you say that object's moving at constant speed, I don't really know. B, yeah, the cars are both moving 1 meter per second north. What's going on there? Because they don't always, right? The car 1 moves 1 meter every second, but car 2 doesn't. And then we're going to see the resolution. I think it's over, see it in actually a couple of places. But notice actually Charlotte, Miles, and James group actually got these totally right. The displacement for the velocity for every second, 0.25 meters per second north, 0.75 meters per second north, 1.25 meters per second north, 1.75 meters per second north. If you take all these four numbers and average them, you'll get 1 meter per second north, right? Like if you take add them up and divide by 4, you get 1 meter per second north. So that's what average velocity, that's why we use the word average in average velocity. Okay. What I want to talk about now is this last question about whether we can talk about the velocity of an object in an instant. And Kevin and the Zits say that at a moment, that object isn't moving, right? If you take a photo of a runner, they wouldn't be moving. But the counterpoint they make, because I asked them to kind of argue against themselves, that the object is still moving and therefore will always be at a velocity. And actually, I think they gave a great example and counterexample because I think it's really good, right? If you take a photo of a runner and then show that to the runner later and ask the runner, hey, remember the time were you moving? Will the runner say, no, I guess not, because the photo is still? No, the runner is going to know they were moving, right? Or like, let's say you're driving in with your parents or whatever in a car and you take a photo of the speedometer. Well, a photo shows just one instant, doesn't it? But if you look at the photo, will it say 0 speed because you took a picture? No. So what that tells us actually is that it must be possible to talk about speed or velocity at an instant. Another group actually made a really interesting argument for why. They said, this is group 1. You can't calculate it with one time because you need to divide 2 points to find the displacement and calculate the velocity. So right, I told you that the way to calculate velocity was you had to subtract 2 different positions to find the displacement and then divide that by the time it took to get the velocity. So what I want to do is I want to talk about, God, I love Kermit the Frog. I want to talk about this idea called instantaneous velocity. And I want to define it as velocity over an infinitesimal time interval. Let me try to give you an idea of what that means. Let's say we have a graph, and it looks like this position time, and I'm not going to draw numbers on it, but like kind of just follow along with me. And it's an object that's speeding up. Okay. At this time, if I want to know, let's say this is like 2 seconds, I could, like you did in class, figure out the average velocity between, let's say, 2 seconds and 3 seconds, or the average velocity between 2 seconds and 1 second. But I could also probably find the average velocity between 2 seconds and 2.1 seconds. And I hope you'd agree that if I found the average velocity between these 2 points, it would be more accurate than finding the whole velocity over this time. But I can actually go further. I can zoom in and I can find, let's see, zoom in, boom, boom, boom. I could make a dot over, let's say, here at like, let's call that 2.05 seconds. I'm not going to try to write that because, my handwriting would be awful. But if I found the displacement in time between these 2 points, I'd get even closer. And I can imagine making a dot even closer and finding the displacement in time between those 2 points. Okay, imagine I did this. Imagine I took 2 dots, 2 points in time, and I tried to make them as close as I could, and then I connected those with a line. Well, here's what that line would look like. Here we go. I just read you this a little bit. If I wanted to find the velocity at 2 seconds, I could draw a dot as close as I possibly could to 2 seconds and find the displacement in time. Well, I could take those 2 points and draw and connect them and form a line. I'm going to try to do my best on that on Jamboard. And here's the deal. It's a line, right? Lines have one slope. So if I want to find the displacement in time between those 2 points, and I want to, which is to say, I just want to find the slope of that line, well, I can find the slope of this line over here, this kind of big line. What I've just drawn is a way to actually figure out the instantaneous velocity, because I just drew a tangent line. It's a line that touches the graph at 1 point. Right? Now, because I said it was 2 points, but like imagine those 2 points were like super duper close together. Imagine they were, going back to my definition, infinitesimally close together because I looked over an infinitesimal time. Okay? So if I did that, then like those 2 points would really be 1. And then I could figure out the slope of that tangent line. And the slope of that tangent line tells us the instantaneous velocity. Exclamation point, because this stuff is super exciting. The slope of a tangent line tells us the instantaneous velocity at that time. Okay. Let's chat about that a little bit in a different context. And the context is this graph. So I have this kind of more formal, like more pretty graph that what I've done is I double click on it and I went into drawing and then I clicked on this button over here. And this button, if you notice, actually let me undo this so I can do it, lets me add a line. Like I can take a line and add it over here. And then I can like move it around. So like I'm gonna show you what I did here. I'll delete this. I can delete this too. I can take a line and I can draw it like this. And notice what I'm doing is I'm kind of trying to make it so that if I take that line and I move it now, it'll touch the graph at exactly that 1 point, but really nowhere else on the graph. And I know it kind of touches a bunch of it, but it's really trying to contain, like it's trying to be at the same slope as the graph. And now what I can do is I can measure the rise and the run for this line itself. And that will tell me the slope of the graph. Okay. Now I had it before, and I want to actually use that version, because in this version I can just look at the rise, which is 14 meters here, minus what is that, 6.2 meters approximately, which is 7.8 meters. And then the run is about, that looks like about 2.5 seconds minus 1.6 seconds, which is 0.9 seconds. And so you noticed that over here, I actually filled that in. I divided that displacement by that time to get the velocity over there. Okay. Now, you might wonder, like, wait a second, but the object didn't actually go from 14 to 6.2 centimeters. Yeah, but remember that the idea I'm using here is that a tangent line is really just drawing a line that connects two dots that are super duper 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 close. And because in a line, I can measure the slope along from any 2 points, and it's going to give me the same slope. I'm just going to make a line nice and big so you can actually view it. So for homework, you're going to finish all this up. You'll get slopes for all the other points. You'll turn it into a graph, and I want you to answer these questions. Okay, I will see you all later.